Assalamu alaikum and good morning. The topic we'll be covering today is electronegativity, basically. It's electronegativity. And the accompanying note for this can be found on AurParho.live under the name, it's called Introduction plus Electronegativity. Colon chemical bonding. That's the name of the note, and you can find it on AurParho.live if you just search for it, and you can go ahead and download that. You can open it up now because it'll be helpful to follow along, as I'll be referring to it multiple times throughout this video. Alright, so let's get started right away. Electronegativity. What is electronegativity basically? And when we talk about electronegativity, there is an associated concept that we also have to consider, which is polarity, which is basically the consequence of different electronegativities of different atoms. So we'll be talking about those, and उसमें फिर हम dipoles के बारे में बात करते हैं, हम relevant partial charges और relevant lone pairs के बारे में partial charges, lone pairs के बारे में बात करेंगे. So basically, a good hefty amount of content. So the electronegativity of an element is the relative ability of each of its atoms to attract the electrons of a covalent bond towards itself. ये नोट में लिखा हुआ है. अब इसका मतलब क्या है? इसका मतलब ये है कि समझें A और B are in a covalent bond, meaning that they share this pair of electrons between their nuclei, which forms a covalent bond. What electronegativity suggests is that if, for example, we'll just take this example, this is not any real value or anything, it's just relative. Let's say, for example, we give the electronegativity of B a value of 5, a relative value of 5, and for A, we give it the value of 1. So its electronegativity value is 1. So B is obviously more electronegative, और इसका मतलब क्या होगा कि its ability to pull these electrons, so this pair of electrons towards itself while maintaining that covalent bond is going to be greater. इसका मतलब since electronegative B की ज़्यादा है, the actual molecule is going to exist something like this. See, so we can see here that it was in this case it was relatively in the middle, but in the second case, which is the actual case, if we apply these electronegativities, the pair of electrons shifts more towards B, so the distance between it and A increases, and the pair of electrons and B, the distance between those decrease. So that's basically what electronegativity is. It is the ability of an atom to pull the shared pair of electrons in a covalent bond towards itself. Just some extra information, it's measured on the Pauling scale. So it's measured on the Pauling scale, which is a scale that goes from 0 to 4, and on this scale, 0 is the least electronegative you can get, and 4 is the most electronegative you can get. And also you should note, you don't have to remember this, eventually you will just recognize this through conceptual knowledge, through conceptual understanding, but fluorine is actually the most electronegative atom. Fluorine is the most electronegative atom, and in general, nonmetals are more electronegative. Nonmetals are more electronegative than metals, generally speaking. There might be some exceptions if you just mess around with particular elements and whatnot, but this is basically what it is. And at this point, you might ask me what determines the electronegativity of each atom, because obviously electronegativities are different between atoms, or there wouldn't be much of a concept to explain. Or the determining factor behind electronegativity is essentially factor determining electronegativity, and the factor is it's one factor that's usually split into two, and I'll explain. अभी समझ आ जाएगा कैसे. The one factor is charge density. Now, charge density itself depends on two other things. It depends on the atomic radius, so basically the size or the volume of the atom, atomic radius. And the second thing it depends on is obviously the nuclear charge. So nuclear, you can imagine that the nuclear charge per unit volume would become the charge density. So the smaller an atom, so the smaller volume it has and the greater charge it has, the more electronegative it will be, the more charge density it will have. So when we taught this in school, we usually taught these two factors, but in the end they combine to form charge density, which is actually what electronegativity depends on. And just to put this out there, the more charge density an atom has, the more electronegative it will be, and the more stronger it will be when pulling electrons in a covalent bond toward itself. Right, so we can take an example. We can take the example of period 2, and more specifically the carbon-fluorine bond. So let's say there's a carbon-fluorine bond, and each of these atoms share an electron and to form the covalent bond. Now, if you look at the sizes and the charges on the carbon versus the fluorine atom, the carbon atom has a significantly greater atomic radius, so it has a greater volume and a greater size than the fluorine atom. And the carbon atom also has 6 protons in its nucleus, and a fluorine atom has 9 protons in its nucleus. So here you can see where I'm kind of going with this. Fluorine definitely has a greater charge density because it has a greater nuclear charge. So it has a greater nuclear charge, and it has a smaller size. Or in this case, you can just call it atomic radius because that's what the size is dependent on. So it has a smaller atomic radius and a greater nuclear charge, hence it has the higher charge density. Now, because it has the higher charge density, it is more electronegative than carbon. Which has 6 protons, which is relatively less than 9, and it is also bigger. So it has less charge density and hence is less electronegative than fluorine. So now that we've established that in a CF bond, in a carbon-fluorine bond, carbon is less electronegative and fluorine is more electronegative, इसका मतलब क्या है? इसका मतलब ये है कि the shared pair of electrons between these two atoms is going to be attracted more towards F than towards C. So in actuality, it's going to exist much closer to F than it does to C, because F is more electronegative, right? This distance is going to be greater than this distance, right? So that is basically the concept of how charge density dictates electronegativity, and how in the end that dictates where the pair of electrons in a covalent bond exists. Also, it's important to note that this notation, which you will commonly see in textbooks and videos and whatnot, and in tests maybe, this shows the movement of a shared pair of electrons. Not exactly the transfer, but it shows the shifting towards one atom in comparison to the other. And then similarly, you have to draw the partial charges. So when the pair of electrons shifts closer towards the fluorine atom, the region of negative charge, so basically the region of electron density around F, will increase and will become partially negative. And similarly, because it's becoming partially negative, there's now less electron density around carbon, so carbon will become partially positive. Separation of charge refers to the attraction of electrons. That's basically what we just did. And when this happens, it's important, when the shared pair of electrons exists closer to one atom than the other, we call this a dipole. we call this a dipole, basically meaning that the electron density has shifted towards one end of a molecule, so it's not equally distributed anymore. And whenever a dipole is formed, usually, there are always exceptions depending on the shape of the molecule, but usually when a dipole is formed, it suggests that the molecule that contains that covalent bond will be polar. Unless, the shape of the molecule is such that the direction of the dipoles, they cancel each other out. And in that case, it is possible for the molecule to have dipoles but still be nonpolar. And in that case, it will have no overall dipole, which is actually what we look at when we talk about polarity of a molecule. And we'll discuss that in a bit. We're getting there. Pauling scale values. There are a few Pauling scale values on the notes. You can go through those. Those are just for your knowledge. They don't provide any conceptual value. Oh, but it is important to note that generally speaking, if the difference in Pauling scale values of two atoms, Pauling scale values of two atoms is greater than 2, then it is likely that they will form ionic bonds. This is because when the difference in electronegativity of two atoms is so great, it's greater than 2, then one atom will definitely not be able to hold on to its electrons, and the other atom will be so strongly pulling towards the electrons that an actual electron transfer occurs instead of just shift in the position of the pair of electrons on the covalent bond. So therefore an ionic compound will be formed. And we won't go into too much detail about this right now. You can look into it more if you want by yourself. And similarly for covalent bonds, for a covalent bond to occur, whether it's polar or non-polar, the difference in Pauling scale values usually has to be less than 1. And this is for covalent bonds to occur. Alright, so now let's move on to the polarity and dipoles in common molecules. And this is where I'll explain how shape affects the overall dipole of a molecule. And at this point is where I'll hope it becomes more clear. So first, let's take like a simple example. Diatomic hydrogen, right? H2. Here you have two H atoms, and they have the exact same electronegativity because they're the same exact atom or the same element. So I mean, even if you consider them to be pulling with the same force, I guess, the pair of electrons in the center, it's not going to go anywhere because the force is equal on both sides. So basically dipoles cancel out and this becomes a nonpolar molecule. On the other hand, let's take an H2O molecule. H2O molecule has an O, an H, and H. Right, it has 2H and O. And O is significantly more electronegative than hydrogen, so electron density shifts upwards. And in this case, you can see that it doesn't cancel out. The electrons are effectively able to shift towards O. The dipole doesn't cancel out, and oxygen becomes more electronegative. Oxygen gets a partial negative charge, and both of the hydrogens get a partial positive charge. And it's also important to note that there's, I always forget this, but there is a lone pair of electrons on the oxygen, which is actually what causes this nonlinear shape. And let's take one more non-polar example. Let's take CO2. CO2 is a linear molecule, meaning that there's one central carbon. There's one central carbon and two oxygen atoms bonded this way. And since oxygen is electronegative, there should be a dipole. However, notice that if one oxygen pulls this way, one oxygen pulls that way, the electron density doesn't end up shifting because the dipoles cancel out. Hence, this molecule ends up being non-polar. Right, so basically, I hope that communicates what I'm trying to do here, that sometimes dipoles cancel out, other times they actually reinforce each other. Like for example here, the dipoles reinforced each other in the vertical direction. It might not be, immediately noticeable because they're diagonal, but they're going towards the same point, hence they're reinforcing each other vertically. So yeah, overall dipoles may not be the same as individual dipoles. It is also important to note, in like we did in this case here, that lone pairs do have an effect on the polarity of a molecule in two significant ways. The first is that they actually act as an area of negative charge, area of electron density. So they do contribute to the partial negative nature of some atoms, area of negative charge. That's one way. The second way in which they can influence molecule polarity and overall dipole is by influencing the bond angles. So like for example, in a molecule like this, let's say A has a lone pair of electrons. The lone pair actually pushes these electrons down, right? It pushes these electrons down, which causes the dipoles, if there were any, to not cancel out, right? So that is one way in which they influence bond angles. So that is another way in which lone pairs on an atom can influence the overall dipole and the molecule polarity. So I hope that kind of explains things as far as electronegativity is concerned. If you had any questions or if something was unclear or I missed something out or I said something wrong, please let me know in the comments below. And if this helped, like and subscribe, and just watch out for more content because hopefully there will be a lot more. Thank you for watching.